This is lesson 10, introducing graphs of proportional relationships. And this is activity 3, matching tables and graphs. This is a long activity in that there are 10 tables to match to 10 graphs. And so I'm going to do the matching for you and then just go through different ways that you can think through how the tables match the graphs and what kind of information you can get out of that. And I'm going to go through the first couple in some detail, and then I'm going to go through the remaining matching graphs and tables just briefly. So in this first one, what I did is I came up with 5 questions to go through to see if the table does match the graph and if they are proportional relationships. The first one, so what are the 2 properties? So if they are proportional relationships, if the 2 properties described are proportional, they will move together through multiplication. So there has to be 2 properties to look for. In this case, the one property is the number of people in a car that are entering a state park. And we actually saw this problem before. So X is going to be the number of people in the car, and Y is going to be the entrance fee. So one property is the number of people in the car. The other property is how much does it cost in total to get into the park. And because this is set up as dollars per person, that gives you a pretty good idea that X is going to be the number of people and Y is going to be the cost, because it's going to be Y per X, or cost per person. And so the first question, what are the 2 properties? Well, those 2 properties are the number of people in the car and then the cost to enter the park. And so the number of people in the vehicle and the cost to enter the park. And if these are the X values, the number of people, label the X-axis number of people in the vehicle. And if these are the Y values, the total cost to enter the park, label the Y-axis as the cost to enter the park. And to figure out if it's a proportional relationship, you look for, first of all, is there a constant of proportionality? So you go through, we've done this before, take the Y value and divide it by the X value and see if there's a constant factor that you're using to multiply X by to get to Y. So Y divided by X, and in this case there's not. So 8 divided by 1 is 8, 5, 4, 3 and a half, basically 3 and a fifth, and 3. So there's not a constant amount that the X value gets multiplied to get to the Y value. So is there a constant factor or a constant of proportionality? And the answer is no to that. Is the graph a straight line? Well, the graph is a straight line, and you could argue that I shouldn't connect the points because you can't have a part of a person enter the park, but I want to connect the points just so that you can see that those points do fall in a straight line. So it is a straight line, but does it go through the origin? So for a proportional relationship, what you're going to see eventually is that it has to be a straight line, and that line has to go through the origin. In this case, it does not go through the origin. And actually, it goes through Y equals 6 because you have to pay $6 for the vehicle. So if the number of people going in the park was 0, you would already owe them $6 if you were somehow to take a vehicle into the park. You know, the point is that when you drive up, you already owe $6 before you've paid at all for any of the number of people in the car. And so it is not proportional. But there actually is a proportional relationship within this problem, and that is the cost per person. So the cost per person is $2. So the park ranger is going to look inside the car, count the number of people in the car. Let's say they see 3 people in the car. They're going to multiply that number times 2. 3 times 2 is $6. And then they're going to add the $6 on for the vehicle to get into the park. So the cost to get into the park is going to be $12. So you go to 3 people, 3 times 2 is $6, and go up to here, but then you're going to add another $6 for the vehicle. Say there are 5 people in the car, so it's $2 for 5 people, 2 times 5 is $10, plus another $6 for the vehicle to get into the park. So there is a proportional part to it, although the overall relationship is not proportional because you end up adding that $6 each time. So to graph these, usually you are given the X value, which in this case is the number of people. So that's the first value you have. and you look at the x-axis and you go down to what the x-coordinate is. Let's say again that it's 3. So you go down the table to 3. You're given 3 people that are in the car. How much does it cost? You go across the x, along the x-axis to the x-coordinate, which is 3. You calculate that it costs $12. So y is going to be the answer to the calculation, usually. So then you move up to the y-coordinate, which in this case is 12, and you place a point there. So this has an x-coordinate of 3 and a y-coordinate of 12. So you find the x-coordinate first, and then you move up the y-axis to where the y-coordinate is. So you're given the x-coordinate, you calculate the y-coordinate. You're given the x-coordinate, and you move up to the y-coordinate based on the calculation. So it's x and then to y. It's x and then to y. The next table and graph that matches is table 2 matches graph B. If you look down the x values, you see 1, 2, 4, 5, 7, and 8. 1, 2, 4, 5, 7, and 8. If you look along the y values, you're going to see that it's 8, 16. So you have to just kind of guess here. 8, yeah, it's about 16, 32. So you can convince yourself in the beginning that this graph matches this table. And so the 5 questions to take a look at: what are the 2 properties in this problem? And those 2 properties are the number of t-shirts and the total cost of the t-shirts that you purchase. So number of t-shirts and total cost of those t-shirts. So the number of t-shirts and the total cost of those t-shirts. And so the x-axis is going to be the number of shirts because it's cost per t-shirt. So it's dollars is the y value and the number of t-shirts is the x value because it's y per x, or dollars per t-shirt. $8 each t-shirt. And so label the x-axis as the number of t-shirts, label the y-axis as the total cost of those t-shirts. And now look to see if there's a constant of proportionality. So if I divide y by x, is there a constant factor that I can use to go from the x value to the y value? And there is. It is 8. 8 divided by 1 is 8, 16 divided by 2, and so on down the columns. You're going to get a constant factor of 8. That is the constant of proportionality. So 8 is the constant of proportionality. It's also called the unit price. It's $8 per t-shirt, and they actually give that to you in the beginning of the problem. And what that means is that if we look at 32 divided by 4 equals 8, that means that 32 is 8 times greater than 4. So 32 is equal to 8 times 4, because there are 8 4s that you can get into 32, or 8 times 4 equals 32. And so yes, there is a constant of proportionality. It's the unit price. Is the graph a straight line? Well, if you connect them, you do see that they fall in a straight line. And again, one could argue I shouldn't connect these points because you can't purchase a part of a t-shirt, but I do want to connect them to show you that it is a straight line, and finally that it does go through 0. Does the line go through the origin, 0, 0? And in fact, it does. So these 3 things taken together: 1 is that there's a constant of proportionality, 2 is that the graph is a straight line, and 3 is that the graph goes through the origin, 0, 0. Those 3 things taken together show you that the number of t-shirts and the total cost of the t-shirts is a proportional relationship. So this is a proportional relationship. That means that if you double the number of t-shirts, if you triple the number of t-shirts, or 4 times, 5 times, 100 times, whatever it is, the cost is going to double, triple, be 4 times, 5 times, 100 times in the same manner. So they're going to move together using multiplication, in this case, using that constant factor of 8. Now, in a proportional relationship, you can go back to what we looked at in the very first unit, which was scale factors. And you can see if you work down the column, that's using the scale factor. So if I double the number of t-shirts from 2 to 4, I'm going to double the total cost from 16 to 32. 4 times the number of t-shirts from 2 to 8, 4 times the cost from 16 to 64. But if you go across each row, you're going to use that constant of proportionality. And that's the usefulness of a constant of proportionality, is that you can use it for every row. That's not true with the scale factor. You have to come up with a different scale factor most of the time for different, going from one row to another row down the columns. So you want to really move towards figuring out what that constant of proportionality is, and that's also going to allow you to write the equation y equals kx, where k is that constant of proportionality. Now remember, to graph them, you're going to be given, usually you're given the x value first. So you go in, you're going to buy 5 t-shirts. So you're given that. You're going to buy 5 t-shirts. And so you find that x coordinate on the x-axis, and then you do the calculation. 5 times 8 is $40. And so then you're going to move up from the x-axis to 40 is the y-coordinate. So this coordinate for this point is 540. The x-coordinate is 5, and the y-coordinate is 40. So 540. For 7 t-shirts, it would be 756. So you go across here to 7, and you go up to 56. So this is table 9, which matches graph C. And in this case, the two properties are the number of cans and the weight, the total weight of those cans. So it says up here, 10 empty aluminum cans weigh 15 hundredths of a kilogram. Well, one aluminum can weighs 15 thousandths of a kilogram. So y divided by x gives you 15 thousandths of a kilogram per can. You're going to see that if you do that division all the way down, what's the value of y divided by x? It is the same. So there is a constant of proportionality, 15 thousandths of a kilogram per can. So the two properties, number of cans and the total, or the weight of those cans. And so label the x-axis the number of cans, because it says it's the number of kilograms per 10 empty cans. So it's y per x, or weight per cans. And so the x-axis, label that the number of cans, and the y-axis, label that the total weight of the cans. And remember, you're usually going to be given the x value, and you're going to figure out what the y value is. So you're given 40 cans. So what's the weight of those 40 cans? We're going to multiply that by 15 thousandths. So 40 times 15 thousandths is going to tell you that it's 60 hundredths of a kilogram, or 6/10ths of a kilogram. But the point here is that there is a constant of proportionality. That is the weight per can, which is 15 thousandths of a kilogram per can. Is the graph a straight line? And in fact, it is a straight line. So you can draw a straight line, and that graph actually goes through 0. If you have 0 cans, then you have 0 weight. And this is one of the reasons, or this is the reason, we talk about proportional relationships going through the origin, 0, 0. Because if you have 0 of one of the properties, then you have 0 of the other property. So if you have 0 cans, then you have 0 weight. So is the graph a straight line? Yes. Does it go through the origin, 0, 0? Yes. It is a proportional relationship. So these three things, there's a constant of proportionality, the graph is a straight line, and the graph goes through the origin, 0, 0. So what that means, once again, is if you double the number of cans, you're going to double the weight. Triple the number of cans, you're going to triple the weight. 4 times the number of cans, the weight's going to be 4 times. So you can work with a scale factor if you go down the columns once again. So 4 times the number of cans from 10 to 40 is going to give you 4 times the weight, 15 hundredths to 60 hundredths, or 6/10ths. But it is better, and it's probably a good idea to do both for a while, but it's going to be more useful to you to figure out what that constant of proportionality is, because then you can apply that to every single row. You cannot do that with the scale factor, because we just did 4 times to go from 10 to 50, you'd have to do 5 times. To go from 20 to 60, you'd have to do 3 times. So you have to use different scale factors. But you can always use the same constant of proportionality, and that also helps you write the equation in which k is that constant of proportionality. So y is equal to kx. And k, in this case, is the weight per can, that 15 thousandths of a kilogram per can. Now to graph it, you're going to graph the x value first. You're going to figure out, okay, I have 25 cans. You're going to move along the x-axis to 25. You're going to figure out what that weight is using the equation or multiplying by 15 thousandths times 25. And you're going to figure out that that's 375 thousandths. So the 25 up to 375 thousandths, which is a point right here. It's just below 400 thousandths or 4/10, and that's the y coordinate. So this is the x coordinate, 25. This is the y coordinate, 375 thousandths. So you graph the x coordinate first, and then the y coordinate second. Okay, table 4 matches graph D. And in this case, you're going to see that this is also a proportional relationship. The two properties says she is planning on serving 1/3 of a cup of rice per person. So this is rice per person. So that's y per x. So that tells you that y is going to be the cups of rice and x is going to be the number of people. So it's the number of people, cups of rice. So the two properties are the number of people, the cups of rice. So the x value is going to be the number of people. So label the x-axis the number of people. And the y value is going to be the cups of rice. So label the y-axis the number of cups of rice. And is there a constant factor? So divide y divided by x. And it's useful to change each of these thirds to an improper fraction. So if you read down them, so it's y divided by x. It's always going to be 1/3, but this is 1/3 divided by 1. 2/3 divided by 2, so that makes sense that that's 1/3. You have two things, you divide it by 2, you're going to get one of those things. This is 1/3. This is 4/3 divided by 4. So if you have 4 of those thirds divided into 4 parts or 4 groups, it's going to be 1/3 per each group. So the answer is 1/3. 5/3 divided by 5 is 1/3. And 2/6 is actually 6/3, which is equal to 1/3. You can factor out the 2's, you get 1/3. All right, so there is a constant of proportionality, and it's the unit serving. How much is going to be served per person? So it's 1/3 of a cup of rice per person. Now, is the graph a straight line? So now you figure out the graph, or you just connect the points. And in this case, you can have a part, well, actually, you can't have a part of a person. I was going to say you can have parts of cups of rice, but you can't have a part of a person. So again, these points really should not be connected, but I do want to show you that they fall in a straight line, and they do go through the origin. Once again, if you have 0 number of people, then you have 0 cups of rice. That makes it proportional. That's part of the elements that you want to look at to see if it's proportional. So straight line, it goes through the origin, 0, 0. So the fact that there's a constant of proportionality, that the graph is a straight line, that the graph goes through the origin, 0, 0, all of those points taken together means that this is a proportional relationship. So what that means is, once again, if you double the number of people, that you double the number of cups of rice you need. Triple the number of people, triple the cups of rice. 4 times the number of people, 4 times the cup of rice. So again, the scale factor, you can work down the column if you want. So if you double the number of people from 2 to 4 people, you're going to double the cups of rice from 2/3 to 4/3. 2 to 6, that's 3 times. 2/3 to, actually this is 6/3, that would be 3 times as well. Or you can use the constant proportionality, which is working across each row. It's more useful to use that constant proportionality, which is 1/3, because once again, you can then use it in the equation where k is equal to that constant proportionality, which is 1/3. It's also the unit serving. So yeah, it makes sense. If I I'm going to serve each person 1/3 of a cup of rice. I have 5 people. It's going to be 5 times that 1/3 or 5/3. So remember to graph it. You're going to work down the column along the x values. Those are what's going to be given to you first, usually, to solve these problems. I have 6 people sitting at this table over there that I have to serve. How many cups of rice do I need? Well, that's 6 times 1/3. So along the graph, you're going to go and find the x-coordinate of 6 along the x-axis. And doing the calculation, it tells you that the y-coordinate is 2 or 6/3. They are the same thing. So then you work up to the y-coordinate of 2, and you would put a point there. So table 4, graph D, cups of rice per person. So table 6 matches graph E and says he measures the time that has elapsed after each lap he runs. So it's going to be time per lap. So y is going to be the time. It's y per x. So y is going to be the time and x is going to be the lap. Y, or time per lap. And so what are the two properties? It's the number of laps that he runs, the column on the right, and, the number of laps he runs, the column on the left, is the number of laps, and the total time that he runs, that he takes to run those laps, which is the time on the right. So number of laps and total time. That means that you want to label the x-axis the number of laps. It is the x value. And that's what you're going to get in the problem first. Oh, gee, I ran 4 laps. How long did it take? It took 9 minutes. You're not going to be given 9 minutes first and then ask how many laps did that take. You're going to be given the number of laps. And then notice he measures the time that has elapsed after each lap. So he's run 5 laps. How much time? So that's the x value. So label the x-axis number of laps and label the y-axis the total time. And it doesn't really say that it's in minutes, but I'm just going to assume that it's in minutes. So total time in minutes. All right, is there a constant factor, a constant of proportionality? So you divide y by x, and in fact, there's not. So it begins at 2, and then the next row is also 2, and you think, aha, maybe there is. But then you go to 3 laps, and it's 2 1/3. It would be 6 divided by 3 to be proportional. This would be 8 divided by 4, but it's 9 divided by 4. This would be 10 divided by 5, but it turns out to be 11 divided by 5. And 12 divided by 6 turns out to be 15 divided by 6. So this time per lap is increasing. So what's happening is that he is getting slower. He's tiring out. So he's taking more time to run the later laps. So is there a constant factor? No, there's not. Is the graph a straight line? No, it's not. You connect each of these points and you see that it's not a straight line. As a matter of fact, it's taking more time to run a lap. So you go from 5 laps to 6 laps. That's taken more time. It's this amount from here up to this amount is the time that it took to run from the 5th lap to the 6th lap. So is it a straight line? No. Does the graph, in this case, it's not a straight line, so I changed that to graph. Does it go through the origin? Well, yes, it does. But it's not a proportional relationship. There's no constant of proportionality. The graph is not a straight line. And the graph, even though the graph goes through the origin, 0, 0, it's not a proportional relationship. And so it looks like he is slowing down as he runs more laps. So again, you're going to take the x-coordinate, find that first. So move along the x-axis to the x-coordinate. Let's say it's 5. And then look at what the table says. It's y-coordinate of 11. So you're going to read up the y-coordinate, the y-axis to 11 and place that point right there. This is table 7 and graph F. And the relationship in this example is between tablespoons of honey and cups of flour. And you know that the x value in this relationship is tablespoons of honey because it says 2 tablespoons of honey for every 8 cups of flour. So this is the 2 right here. So it's 2 tablespoons of honey for every 8 cups of flour. And so the two properties in this problem are tablespoons of honey and cups of flour. So if you take the tablespoons of honey, and actually if you take the cups of flour and you divide that by the tablespoons of honey, so y divided by x, so how much flour is there per tablespoon of honey? And you get an answer of 4. So 8 divided by 2, 12 divided by 3, and so on. So you always get an answer of 4. So that is a constant of proportionality. It's a constant factor, and it's actually the unit rate. So how many cups of flour do you need for 1 tablespoon of honey? You need 4. So it's 4 cups of flour per 1 tablespoon of honey. And what that also says is that this ratio of 8 divided by 2 is the 8 is 4 times the amount of 2. So 8 is equal to 4 times 2, because there's 4 2's that you can for every 8 cups of flour. Likewise, 12 is 4 times 3, and 24 is 4 times 6. So you use that to set up the equation y divided by x, or y over x equals k, and so therefore y is equal to k times x. It's that multiplication, that constant factor. And so yes, there is a constant factor in this problem. It's the constant of proportionality. It's the unit rate, 4 cups of flour per 1 tablespoon of honey. The graph is a straight line. And that line also goes through the origin 0, 0. So the combination of a constant of proportionality, the graph being a straight line, and the line goes through the origin, or 0, 0, all of those things together means that this relationship between flour and honey is a proportional relationship. So what that means is that they are related through multiplication. So if you double the amount of honey, you double the cups of flour. Triple the amount of honey, triple the cups of flour. 4 times the amount of honey is 4 times the amount of flour. So those are scale factors. If you double the amount of honey from 3 to 6, you're going to double the amount of flour from 12 to 24. So as you work down the column, you're using scale factors. 5 times the amount of honey. 2 times 5 is 10. 5 times the amount of flour. 8 times 5 is 40. So that's using scale factor. Now you have to use a different scale factor most of the time. But if you use the constant of proportionality, that's always the same factor. It's constant. It doesn't change. And so that's going across the rows. So 2 times 4 is 24. 7 times 4 is 28. So that's the reason to use the constant of proportionality is you can use it in every case, and then you can use it to set up the equation. Now to use the graph, you go to the x value first. That's the x coordinate. That's the thing that's given to you. Gee, I have 3 tablespoons of honey here. How much flour do I need for this recipe? And then you read across using the equation to get the answer. 3 times 4 is equal to 12. You need 12 cups of flour. So you find the x-coordinate on the x-axis first. You go out to the x-coordinate, which in this case, let's say it's 6. And then you read up the y-coordinate till you get to this line. Or if you're graphing it first, you realize it's 24. So you go up to 24 and place a point there. Or if you're reading off the graph, gee, I have 6 tablespoons of honey. How much flour do I need? Then you read up to the graph and then read over and see that it's 24 cups of flour. This is table 3 and graph G. And I thought this was the most interesting of all of the problems in this activity, because this uses a formula or an equation that you are familiar with, that you've seen before. Many of you have seen before. And so this is converting temperatures from degrees Celsius to degrees Fahrenheit. So you're going from Celsius to Fahrenheit. So that means the x values are going to be degrees Celsius and the y values are going to be degrees Fahrenheit. So what we're going to do is take a look at how they came up with this equation. So I'm going to go through, or how you use the equation, what's happening as you use the equation, and then a little bit at the end of how they came up with that equation. So that's degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32 degrees. So again, you're given the degrees Celsius, so that's X. You're going to calculate the degrees Fahrenheit, so that is Y. All right, so once again, the properties in this problem are degrees Celsius and degrees Fahrenheit. And so then you can look at the ratio or the division of Fahrenheit by Celsius and see if you get a constant of proportionality. And you don't. So the first one is 32 divided by 0. And the answer to that problem is whenever you divide something by 0, there's no result. You cannot divide a value by 0. So this is undefined. I think that's the symbol for undefined. So 32 divided by 0 is undefined. There is no answer for that. But then you get out to 50 divided by 10, 68 divided by 20, and you see that there is no constant of proportionality. So to graph it, you label the x-axis degrees Celsius. That's what you're going to be given in the beginning. So let's say it's 30 degrees Celsius. You use the formula. You figure out that it's 86 degrees Fahrenheit. So you go across here, 30 degrees Celsius. If you're using the graph, if the graph is already given to you, then you'd read up to this line, to that point right there, and you'd read over, and you'd see that that is 86 degrees Fahrenheit. Whereas if you were graphing it, you'd use both of the values on this table. So you'd go over to 31st, the x-coordinate, then go up to 86, and you'd place a point there. And then you'd go to 40 and place a point there, and go to 50 and place a point there. And so the graph is a straight line. So what that means, when you see a graph that's a straight line, but it does not go through the origin, so it's no as far as does the line go through the origin or 0, 0, that means it's not proportional, but there is a part of that relationship that is proportional. It's just that the whole relationship between degrees Celsius and degrees Fahrenheit is not proportional. So let's take a look at that just for a moment. So is there some other relationship? In fact, there is. So if you just forget about the 32 degrees for a moment, and you look at what's going on between degrees Fahrenheit and degrees Celsius, you see that every 10 degrees, there's an increase of 18 degrees. So Celsius increases 10 degrees, Fahrenheit increases 18 degrees. Celsius increases another 10 degrees, Fahrenheit increases another 18 degrees. Another 10 degrees, another 18 degrees. So that relationship, 18 divided by 10, is the same as 9/5. 18 divided by 10 is equivalent to the fraction 9/5. Well, there's the 9/5 right there. So the beginning of the conversion from degrees Celsius to degrees Fahrenheit is 9/5 the degrees Celsius, and then you have to add the 32 degrees. So you figure it out and then add the 32 degrees. So this is an increase of 18 degrees. You go over 10 degrees, up 18. Go over 10 degrees and up 18. Go over 10 degrees, up 18. Over 10 degrees and up 18. So what does that look like? First of all, remember how you graph these things. You're going to use the x-coordinate, and you're going to go along the x-axis, which are degrees Celsius, and then you're going to read up the y-axis till you get to, once again, if it's 30, until you get to 86 degrees. So you read across and say it's 86 degrees, or if you're graphing it, you place a point at 86 degrees. But the beginning value is usually the x-coordinate. Not always, but most of the time you're going to read the x-coordinate first and then the y-coordinate. So the coordinates for this point right here are going to be 30, 86. So you write it first 30, and then you write comma 86 inside parentheses. So that's the coordinates for this point right here, 30, 86. All right, so what's going on as you use the equation? Let's look at that part first. So it starts out at 9/5 of 10 degrees. So you're given 10 degrees. What's 9/5 of 10 degrees? Well, divide these 10 degrees into 5 equal parts, 1, 2, 3, 4, 5, and divide the next 10 degrees into 5 equal parts, 1, 2, 3, 4, 5, and count up 9/5 because it's 9/5 of that 10 degrees. Well, this is 5/5, so that's the 10 degrees. 6, 7, 8, 9. So 18 degrees is 9/5 of 10 degrees. So that's the first part of the equation. It's 9/5 of the degrees Celsius. So you take that degrees Celsius, whatever it is, and imagine dividing it up into fifths and counting out 9 of those fifths. And then what do you do next? You add the 32 degrees, and that gets you up to, in this case, 50 degrees. So 18 plus 32 is 50 degrees. Well, what does 20 degrees look like? Well, take the 20 degrees. So this is 0 degrees to 20 right here. So take that 20 degrees and divide that into fifths. Well, since it's twice as much, then every 2/5 of 10 degrees is 1/5 of 20 degrees. So this is 1/5, 2/5, 3/5, 4/5, 5/5. But notice it's every 2 degrees of it's every 2/5, of the 10 degrees. So it's 1, 2, 1/5, 1, 2, 2/5, 1, 2, 3/5, 1, 2, 4/5, 5/5, 6/5, 7/5, 8/5, and then 9/5. So this is 30 degrees, 32, 34, 36 degrees. So 20 degrees, 9/5 of 20 degrees. And you can look at it and see that 20 divided by 5 is 4. 4 times 9 is 36. So that gets you to 36 degrees. What do you do next? You add that 32 degrees. So that gets you up to a temperature of 32 plus 36, which is 68 degrees. And one more. What happens if you're working with 30 degrees? Well, 30 degrees divided by 5 is 6 degrees, and 6 times 9 is going to be 54. But you can look at it as dividing that 30 degrees up into fifths. Well, 30 divided by 5 is 6. So it's going to be 2, 4, 6 degrees. It's 1/5. Now notice it's 3 of the original fifths. 3 of these 1/5 for 10 degrees. So 1/5, 2/5, 3/5 is 2, 4, 6 degrees, or 1/5 of 30 degrees. So 1, 2, 3, 2/5. 1, 2, 3, 3/5. 1, 2, 3, 4/5. 1, 2, 3, 5/5. So 30 divided by 5, so 30 divided by into fifths is 6 degrees each part. And then you want to go up 9/5. So you need, this is 5/5, 6/5, 7/5, 8/5, and 2, 4, 6 is 9/5. And this gets you out to 50 degrees, 52 degrees, and 54 degrees. So 9/5 of 30 degrees is 54 degrees. And what do you do last? Is you add that 32 degrees. So 54 degrees plus 32 degrees gets you up to 86 degrees. So this point right here is 86 degrees. Now notice that the 9/5 of the degrees Celsius is a proportional relationship. It falls on a straight line, and it goes through the origin, 0, 0. So if you double the degrees Celsius from 10 degrees to 20 degrees, you double the degrees Fahrenheit from 18 to 36, or triple it from 10 to 30, you triple it from 18 to 54. 3 times 18 is 54. But then you have to go back and add the 32 degrees, and that's what makes the relationship not proportional anymore, is adding that 32 degrees. But it does fall on a straight line, just no longer goes through the origin, 0, 0. So here's the formula once again. So now hopefully you can see it a little bit better. It's 9/5 of that degrees Celsius. So you're dividing that degrees Celsius up into 5 equal parts. And then you're taking 9 of those fifths. Then you're adding 32 degrees to it. So how did they come up with this formula in the first place? Well, they had the scale for Fahrenheit in the beginning. And they knew that 32 degrees was freezing for Fahrenheit, and 212 degrees is boiling for Fahrenheit. Well, those numbers are not very useful. They're odd numbers to work with. And there was a move towards the metric system. So they wanted everything in powers of 10. So 100 is 10 to the second power. So it is a power of 10. So everything based on tens. And so they decided we want this scale for temperature to be from 0 freezing to 100 degrees for boiling. So we're going to make this scale degrees Celsius. We're going to make it from 0 to 100. Well, the first part's pretty easy. Let's subtract the 32 degrees. So from the degrees Fahrenheit, so now we're going to go the other way for a moment. So from degrees Fahrenheit, subtract the 32 degrees. So you're going to get to 0 here. But then you have to subtract that 32 degrees from 212. Well, what's 212 minus 32? It is 180 degrees. So now this 180 degrees is 10/18. 100 is 10/18 of 180, which is the same as 5/9. So now we're using the reciprocal because we're going from degrees Fahrenheit, degrees Celsius. So it's 5/9 of 180 is that 100 degrees. Well, to go back the other way, you have to add the 32 degrees, and you have to multiply the degrees Celsius by 9/5. Actually, you multiply degrees Celsius by 9/5 first. So that takes 100. 9/5 of 100 is 180. And then you're going to add 32. 180 plus 32 would be this 212 degrees. So now hopefully you can at least see the idea. You might not fully understand it, but there's an opportunity here for you to at least see the beginnings of how people develop formulas. There's no magic. It just makes sense what they're doing. So this is the formula for converting or changing degrees Celsius to degrees Fahrenheit. So these are the x values, and degrees Fahrenheit are the y values. This is table 1 and graph H. I thought this relationship was interesting as well. So this is a relationship between buying t-shirts and how much you pay for purchasing those t-shirts. And the interesting part is that the second t-shirt is half price. So if you buy 2 t-shirts, you pay full price for 1 t-shirt. That in this case is $10. And then you pay half price for the second t-shirt. That would be $5. So if you're buying 2 t-shirts, you're going to pay $15. So the x value is the number of t-shirts. The y value is the total cost of those t-shirts. So the two properties are number of t-shirts and the total cost of those 2 t-shirts. Now, is there a proportional relationship? So you take the total cost and you divide it by the number of t-shirts. So you're getting number of dollars per t-shirt. So if you buy 1, you pay $10 for that 1 t-shirt. If you buy 2, you pay $7.50 for those 2 t-shirts per t-shirt. Total of $15, but $7.50 per t-shirt. You buy 3, that's $8.33 per t-shirt. You buy 4, that again is 7.5. So 7 2/4 is the same as 7.5. So you buy 4 t-shirts, you pay $7.50 per t-shirt. You buy 5, pay $8 per t-shirt. Buy 6, you go back to 7.5. This is $7.50 per t-shirt. So there's something interesting going on there. So the number of t-shirts is the x value, so that's what you're going to label the x-axis. And the total cost is the y value, so that's what you're going to label the y-axis as total cost. Is there a constant factor? No, there's not. There's no constant of proportionality. Is the graph a straight line? No, it's not a straight line, but the graph does go through the origin 0, 0, because if you've bought 0 t-shirts, then you're going to pay 0 money. But it's not proportional. No constant of proportionality, not a straight line, even though the graph does go through the origin. Now, is there some other relationship going on? But first, let me remind you that you're going to read down the x values down the column first. Those are the x coordinates, and then you're going to read up to the graph to either graph it if you have these values, or if you're trying to figure out what these values are and you have the graph, you read up to figure out that if you buy 4 t-shirts, it's going to cost you $30. So then you read over to the y-axis and get the y coordinate. So it's the x coordinate first, then you read up, and it's the y coordinate second. Now there is an interesting relationship. It looks like it alternates $10, $5, $10, $5. So you pay $10, and then you add $5 for the second t-shirt. Pay another $10 for this third t-shirt. 15 plus 10 is 25, and $5 for the fourth t-shirt. pay another $10 for the 5th t-shirt, another $5 for the 16th shirt. So it looks like every even number of shirts is $7.50 per shirt. That's what we see here, 7.5, 7.5, 7.5. This is where graphing can be helpful to you. If you look at the graph and if you draw a line from the origin through each of these points, you see that they fall in a straight line. So every other number of t-shirts falls on this straight line. So that part is proportional. That's $7.50. So if you purchase an even number of t-shirts, you're going to multiply that even number times 7.5 to get the total cost. If you purchase an odd number of t-shirts, then you're going to multiply the even number, so one less, you're going to multiply that by 7.5 to get that cost, and then you're going to add $10 to that, because that last t-shirt, if it's an odd number of t-shirts, that last t-shirt costs you $10, not $7.50. So even number of t-shirts, that is a proportional relationship, $7.50 per t-shirt, but then an odd number of t-shirts, it's the odd number minus 1 to get an even number. That's $7.50 for that number of t-shirts, plus $10 for that last t-shirt. So there is a proportional part to this, but the entire relationship is not proportional. Interesting problem. This is Table 8 and Graph I. And this is a relationship between the number of minutes that it takes this girl to fill her fish tank with the number of gallons that flow into the fish tank given that number of minutes. So it's going to be gallons of water per minutes of time. And it tells you that she is, the chart shows the gallons of water after so many minutes. So you're going to begin with the number of minutes. So X is going to be the number of minutes, and Y is going to be the number of gallons after you have filled the tank for that many minutes. And so the two properties, minutes, the X value, and gallons of water is going to be the Y values. And so label the axis. The X-axis is the number of minutes. The Y-axis is the gallons of water given that time. And so is there a constant of proportionality? So you take Y and you divide it by X, and yes, there is. So it's 1 6/10 gallons of water per minute. It's 1 6/10 gallons of water times 2 for 2 minutes. 1 6/10 gallons of water times 3 for 3 minutes. 1 6/10 gallons of water times 4 for 4 minutes. And 1 6/10 gallons of water times 5 for 5 minutes, and so on. So you're going to read down the X values, read across the X-axis, and then read up to the Y coordinate, which is on the graph, to get the total number of gallons that it fills in that number of minutes. So in 3 minutes, it fills 4 8/10 gallons of water. So this is 4, this is 5 right here. This point is just a little bit below the 5, or at 4 8/10. So yes, there is a constant proportionality. It's 1 6/10 gallons of water per minute. That's called the unit rate. And the graph is a straight line, and it goes through the origin, 0, 0. So these points taken together, constant proportionality, graph is a straight line, it goes through the origin, 0, 0. That is a proportional relationship. So if you double the number of minutes, you're going to double the number of gallons. Triple the number of minutes, triple the number of gallons. 20 times the number of minutes, 20 times the number of gallons. So once again, that's using scale factors. You go down the columns, you're using a scale factor. So 5 times the minutes is 5 times the amount of water. 5 times 1 6/10 is 8. On the other hand, you can use the constant of proportionality and work across the rows. So each one of these number of minutes gets multiplied by 1 6/10 to get the value for the gallons of water. That also fits the equation y equals kx. So y equals 1 6/10 times whatever the value of x is, or whatever the number of minutes is. So proportional relationship, 1 6/10 gallons of water per minute. All right, this last relationship, it's table 10 and graph J, is not a proportional relationship. And you can see from these points that it doesn't not form a straight line, although it's going to go through 0. So this is the relationship between the area of a square and the length of its side. So you're given the length of the side, which is going to be x. You're going to calculate the area, which is going to be y. And so the two properties, the length of the side is x, and the area of the square is y. So you're going to label the x-axis the length of the side, and you're going to label the y-axis the area for that square, given this length of the side. And so if you divide the area by the side, you're going to get an interesting pattern. So the area of one square unit divided by 1 is 1. 4 divided by 2 is 2. 16 divided by 4 is 4. 25 divided by 5 is 5. So what you're doing is you're getting an answer for what you are dividing by. So you're dividing by the length of the side, and you get the answer for the length that is the length of that side. So what that means is that 5 times 5 is going to give you the area. 7 times 7 is going to give you the area. 10 times 10 is going to give you the area. So that's the length of the side times the length of the side equals the area. So that's the formula that you have been shown before. Area of a square is equal to the side times the side, and we write that as side to the power of 2. Remember, the common word for that power of 2 is squared. So it's the side squared because it forms a square. So is there a constant of proportionality? No, there's not, but there is an interesting relationship. Is the graph a straight line? No, it's not. Does the graph go through 0? Yes, it does. But since it's not a straight line, and since there's no constant of proportionality, it is not a proportional relationship. This actually has an interesting name in that it's based on using an exponent. So rather than a proportional relationship, this relationship is called an exponential. Exponent is the 2. So this is an exponential relationship. All right, interesting relationship. We'll have lots more to say about that, especially next year in 8th grade. So I put a table together that summarizes the relationships in these tables and graphs that we just got done doing. So the first 5 listed are the proportional relationships. So tables are listed here, and the corresponding graphs are listed here. And students should practice just saying these words. So table 2, graph B is t-shirts at $8 per t-shirt. So it's the relationship between dollars and t-shirts. Those are the two properties. Or 15 thousandths of a kilogram per can. So cans weigh 15 thousandths of a kilogram per can. People served are 1/3 of a cup of rice per person. Tablespoons of honey is 4 cups of flour per 1 tablespoon. So these are unit rates. So what's happening per unit, per t-shirt, per can, per person, per tablespoon, and the last one's per minute. 1 6/10 gallons of water per minute. The next 3, a portion of the relationship is proportional, but not the whole relationship. So in people entering the state park, it was $2 per person, but the entire entrance fee is not proportional because you have to add that $6, or it's 9/5 of a degree Celsius per degree Fahrenheit. But then you have to add that 32 degrees to get to the final degrees Fahrenheit. But it increases 9/5 degrees Celsius for every, it increases by 1 degree Fahrenheit, which is 9/5 degrees Celsius. And finally, the number of t-shirts increases at $7.50 per t-shirt, but then every odd number t-shirt, you have to add another $10 to get that final t-shirt if you're buying an odd number. And finally, there are 2 relationships that there's no proportional relationship at all, no portion of it, nothing. So one is where the runner is slowing down. They're not even slowing down at a constant rate. So it's tough to see a mathematical relationship there at all, other than they're slowing down per time. And the last one is the formula for the area of a square. This is called an exponential relationship because it's increasing based on the square of the length of the side. And so the area, what you see in an exponential relationship is the area increases very fast compared to the length of the side. That's why it's that curve that's going up very quickly as you get larger and larger lengths of sides.